and unification of electricity and magnetism had led to the remarkable realization that light was an electromagnetic wave. Spurred on by the power and reach of these new theories, physicists began using them to address some of the big unsolved problems of the day. One such problem involved explaining how hot objects emit light. It was well known that if you heat a lump of metal, it will first glow dull red, then orangey red, then yellow, and eventually bluey white at the same time as getting brighter. Physicists wanted to explain how the intensity or brightness of the emitted radiation related to the wavelength or color. They realized that this would involve understanding how matter, the lump of metal, interacts with radiation, the light emitted, at a fundamental level. However, when Maxwell's theory was used in conjunction with classical thermodynamics to calculate the emission profile of a hot object, it predicted that all such objects should be emitting an infinite amount of energy at small wavelengths or high frequencies. Because high-frequency light was dubbed ultraviolet light, and because this prediction was clearly problematic, this issue became known as the ultraviolet catastrophe. It represented a complete failure of classical physics, and it was in attempting to solve this problem that Max Planck was forced to introduce the revolutionary concept of energy quantization, the idea that energy is transferred discretely in chunks rather than continuously. After Planck's work on this topic, the world would never be the same again. In order to properly understand Planck's solution to the problem and why this represents such an important turning point in the history of science, we first need to understand the cause of the problem. And to understand the cause, we need to start with some basics. When you shine light on an object, some of it may be reflected, some of it may be transmitted, and some of it may be absorbed. Darker objects tend to absorb more of the light incident upon them and reflect less than lighter objects, which is why they appear dark in the first place, but also why they tend to heat up more quickly. Think about how black surfaces heat up in the summer compared with white surfaces. An object that absorbs all of the light incident upon it is referred to by physicists as a black body, for obvious reasons. If the temperature of a black body is less than the temperature of the environment in which it is placed, then it will continue to absorb energy from the environment until it has reached the same temperature, at which stage it is said to be in thermal equilibrium. If, however, the black body has a temperature which is higher than its surroundings, then it will radiate energy away until it has lowered its temperature sufficiently to reach thermal equilibrium. Therefore, a black body is not only a perfect absorber of radiation, but also a perfect emitter of radiation. Furthermore, experiment shows that the wavelength intensity profile of a black body has a universal character, which does not depend on the shape or composition of the black body, but only on its temperature. It is this relative simplicity that makes the black body highly appealing to physicists and the logical starting point for any inquiry into the radiation properties of hot objects. An example of a real black body studied by physicists is called the Jeans cube, named after the physicist Sir James Jeans, who, along with Lord Rayleigh, provided one of the first attempts to explain the radiation emitted from a black body. A Jeans cube can be thought of as a cubic metallic box with a very small hole in one of the sides. Radiation incident upon the hole from the outside will enter the cube and reflect back and forth off the walls until it is absorbed. Given that the hole is very small, only a tiny fraction of the radiation inside the cube will ever escape back through the hole. Therefore, from the hole's perspective, essentially all radiation incident upon it will be absorbed, and therefore the hole acts like a black body. We can also consider the reverse process, in which the walls of the cube are uniformly heated to some temperature, such that the walls start emitting radiation and filling the cube. Given that a small fraction of this radiation will then escape through the hole, we see that the hole acts like an emitter of radiation. Since we have already established from the absorption properties of the hole that it behaves as if it is a black body, it follows that the radiation emitted from the hole should have the intensity profile of a black body. Furthermore, since the hole is simply sampling the thermal radiation inside the cube, it is clear that the radiation inside the cube should also have the wavelength intensity profile of a black body. Groundbreaking experimental work into the radiation properties of idealized black bodies was carried out by Otto Lummer and Ernst Pringsheim, and these experiments provided valuable data for theoretical physicists to investigate. The experimental work involved measuring the spectral radiance of the black body as a function of wavelength. This resulted in characteristic curves which varied with temperature. The lower the temperature, the flatter the curve. The spectral radiance is defined as the energy per second, per unit area, per unit wavelength, which is simply the intensity per unit wavelength. And since intensity is defined as power per unit area, it follows that the units of spectral radiance are watts per cubic meter. To find the intensity from one of these graphs, you simply have to find the area beneath the curve. In other words, the intensity is the integral of the spectral radiance with respect to wavelength. Experiments like these revealed patterns in the data. In particular, two striking empirical laws emerged. The first of these was the Stefan-Boltzmann law, which related the intensity of the emitted radiation with the temperature. You can clearly see from the graph that as the temperature increases, the area under the corresponding curve increases, and therefore the intensity increases. The Stefan-Boltzmann law quantifies this relationship and says that the intensity is proportional to the fourth power of the temperature. The second empirical law is the Wien displacement law, which relates the wavelength corresponding to peak spectral radiance with the temperature. As the temperature increases, the wavelength corresponding to maximum emission reduces. This fits with what we've already seen when heating a lump of metal. As the temperature of the glowing metal is increased, its colour changes from red to orange to yellow, which corresponds to shorter and shorter wavelengths of light, and this is encoded in the Wien displacement law. Although the Stefan-Boltzmann law and Wien displacement law provided valuable insights into black body radiation, theoretical physicists wanted more. Firstly, they wanted to know what the spectral radiance function was. And secondly, they wanted to be able to derive an expression for the spectral radiance using the known laws of physics. And so this is what Rayleigh and Jeans did. They turned their attention to the theoretical study of radiation inside the Jeans cube and applied the best theories of the day to tackle this problem. So, what were the known laws of physics? Given that Rayleigh and Jeans wanted to study the radiation properties of a black body, it made sense that they used the highly successful laws of electromagnetism, and in particular, the recently discovered properties of electromagnetic radiation as elucidated by James Clerk Maxwell. According to Maxwell, light consists of a self-propagating electromagnetic wave that travels at the speed of light through a vacuum. Rayleigh and Jeans also turned to the statistical laws of thermodynamics as put forward by Ludwig Boltzmann. According to Boltzmann, the temperature of an object is simply a statistical average of the energy of the particles comprising the object. Armed with Maxwell's electromagnetic waves and Boltzmann's statistical thermodynamics, Rayleigh and Jeans were confident that they could successfully derive the spectral radiance function for a black body. They just needed a clear strategy. Firstly, they realized that it would be more useful and simpler if they specified the spectrum of radiation inside the Jeans cube in terms of the energy density rather than the spectral radiance. And so this is what we are going to do. The energy density is simply the energy contained in a unit volume of the cube at temperature T in the frequency interval between F and F plus dF. Once the energy density has been established, the spectral radiance can be calculated very simply, since the spectral radiance and energy density are proportional to each other. In fact, the spectral radiance is equal to C over 4 pi times the energy density, and we'll return to this result later. Okay, but how do you find the energy density? The approach of Rayleigh and Jeans was threefold. Firstly, you need to count the number of electromagnetic waves that fit inside the cube. Secondly, you need to calculate the average energy of these waves when in thermal equilibrium. And finally, you combine these two results to find the energy density for a particular range of frequencies. So let's do this. To begin with, we need to understand how to mathematically describe waves, since we are going to describe the radiation inside the cube in terms of electromagnetic radiation, which, as already discussed, consists of waves. We can describe a wave travelling to the right using the following sine function. Here, y represents the displacement of the wave for a given x-coordinate and time coordinate. Since the largest possible value of the sine function is 1, we see that capital A represents the amplitude, and this is the maximum possible displacement. So, if for example this was a wave on a rope, A would represent the maximum height that the rope moves away from equilibrium position. The minus sign tells us that the wave is moving to the right, and if we let time flow, we can see this. The constant k is referred to as the wave number, and it's defined as 2 pi over lambda. It represents the spatial frequency of the wave. On the other hand, omega is simply proportional to the frequency of the wave, and that's the temporal frequency, i.e. the number of complete waves passing a point each second. Now we can likewise write down an expression that describes a wave moving to the left, and you see that the minus sign has been replaced with a plus, and this causes the wave to move to the left. So what would happen if we had a right moving wave encountering a left moving wave in the same region of space? Well, in that case, we would refer to the principle of superposition, which states that the net displacement at a location in space is simply the sum of the individual displacements at that point. So if we wanted to find the net displacement due to our right moving wave and left moving wave passing through the same point in space, we simply add the individual displacements. Now, we can simplify this expression by using some trigonometric identities, in particular sine of a plus b and sine of a minus b. If we add these two trig identities together, then we find this purple expression, sine of a minus b plus sine of a plus b equals 2 sine a cos b. Now if we match up terms, we see that a can be identified with kx, and b can be identified with omega t, and therefore the net displacement can be written as 2a sine kx cos omega t. So what does this look like? Well, we can visualize it with the following animation. You see that the left and right moving waves add together to form the green wave. And if we remove the left and right moving waves and just focus on the net displacement, we get the following stationary wave pattern. It's called a stationary wave pattern for obvious reasons, because the pattern isn't moving left or right, it's just moving up and down. So, how does this relate to the electromagnetic radiation inside the Jeans cube? Well, let us assume that the Jeans cube is aligned along an x, y and z axis, and that the length of each side of the cube is L. Then the electromagnetic radiation reflecting back and forth can be analysed into 3 components. Consider the x component. All the radiation along this component which is incident upon the wall is reflected by it, and the incident and reflected waves combine to form a stationary wave along the x direction. Since the electromagnetic radiation is a transverse vibration, with the oscillating electric field perpendicular to the propagation direction, and since the propagation direction is perpendicular to the wall, it follows that the electric field is parallel to the wall. However, a metallic wall cannot support an electric field parallel to the surface, since electric charges can always flow in such a way as to neutralize the electric field. Therefore, the electric field must be zero at the walls of the container. That is, the stationary wave associated with the x component of the radiation must have a node, aka zero amplitude, at x equals 0 and x equals L. These conditions put a limit on the possible wavelengths and therefore frequencies of the EM radiation inside the cube. Clearly, the same also applies to the y and z directions. To see how this works mathematically, we need to first determine an expression for the stationary electric field pattern inside the cube. But this is easy. because we have already seen that a stationary wave pattern is described by the following function. And now we just need to replace the displacement y with the electric field strength E. We can now apply the boundary conditions to our stationary wave function. For example, we know that when x equals 0, we are located at the side of the cube, and therefore the electric field strength must be equal to 0. Why? Well, for the case x equals 0, we see that this is satisfied because sine of 0 is equal to 0. However, we also know that when x equals L, we are at the edge of the cube, and therefore the field strength must also be equal to 0. Now, if we set x equal L in the stationary field function, we see that this will only be 0 if sine of KL is equal to 0. And that this will be true whenever KL is an integer multiple of pi radians. By rearranging this expression, we see that K is equal to n pi over L. Now, if we combine this with the definition of K which I mentioned earlier, K being equal to 2 pi over lambda, where lambda is the wavelength, then you can see that we can rewrite the wavelength as 2L over n, where n is an integer, 1, 2, 3. What is this telling us? It's telling us that the wavelength can only take particular values. Now, if we rewrite this in terms of the frequency, we see that the frequency of the wave can also only take certain integer values. So let's see what this looks like. So imagine we're focusing on just the x direction. Here are the two sides of the cube, separated by a distance L, and we know that the wavelength is given by 2L over n, where n is an integer. So when n equals 1, we see that the wavelength is given by 2L. What about when n equals 2? Well, in that case, the wavelength is given by L. And we can carry on. N equals 3, n equals 4, n equals 5, and n equals 6. So we see that only certain wavelengths can fit inside the cavity, or the cube. Now, we also know that we can write an expression for the frequency, so adding the frequencies for each of these cases, we see that the frequencies also consist of certain integer values. We can represent these allowed values of frequency in terms of a diagram consisting of an axis on which we plot a point at every integral value of n. Such a diagram allows us to count the number of allowed states in any given frequency range. For example, we can specify the distance d from the origin as 2L over c times the frequency. We can then calculate the number of allowed states in the frequency range f to f plus df by looking at the difference in distance from the origin. Since the points are distributed uniformly along the n-axis, it is apparent that the number of points falling between the two limits will be proportional to df, but will not actually depend on f. We can see this explicitly by calculating nf df, which represents the number of states in the interval df. Now this is simply 2L over c f plus df minus 2L over c f, which is equal to 2L over c times df. Now, we need to multiply this by an additional factor of 2, since for each of the allowed frequencies, there are actually two independent waves corresponding to the two possible states of polarization of the electromagnetic wave. So, our final answer for the density of states is nf df equals 4L over c times df. Now, this example provides us with a framework for how we might calculate the number of allowed standing waves in the three-dimensional Jeans cube. But before we get ahead of ourselves, let's first look at a simple generalization to two dimensions. Let's now focus on the x and y dimensions of our cube. We will consider radiation of wavelength lambda propagating in a direction defined by the two angles alpha and beta, as seen in the diagram. The radiation in this arbitrary direction must form a stationary wave, since we've already seen that the x and y components form stationary waves. The diagram indicates the locations of some of the fixed nodes of this standing wave by a set of lines perpendicular to the propagation direction. The distance between these nodal lines of the radiation is half a wavelength, as is true for all stationary wave patterns. We've also indicated the locations on the two axes of the nodes of the x and y components, as well as the corresponding wavelengths along the x and y axes. Looking at the geometry of this diagram, we see that lambda over 2 is equal to lambda x over 2 cos alpha, which we can simply write as lambda equals lambda x cos alpha. Rearranging this expression, we find lambda x equals lambda over cos alpha. We can do a similar thing in the y direction, lambda equals lambda y cos beta, which we can rearrange to find lambda y equals lambda over cos beta. We can now use the relationship we derived earlier, which links the wavelength to the length of the box and the integer n. Specifying this in the x direction, we find lambda x equals 2l over nx, and this means we can write nx equals 2l cos alpha over lambda. Likewise, in the y direction, we can write ny equals 2l cos beta over lambda. This pattern suggests a natural generalization to 3D, where we write lambda z equals 2l over nz, and therefore nz equals 2l cos gamma over lambda, where gamma would be the angle between the wave normal and the z-axis. If we now consider nx squared plus ny squared plus nz squared, we get the following expression, 2l over lambda all squared multiplied by this expression inside the bracket. But we know that cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1. This is just the three-dimensional version of Pythagoras' theorem. And so nx squared plus ny squared plus nz squared is simply equal to 2l over lambda all squared. If we rearrange this, we find that lambda equals 2l divided by the square root of nx squared plus ny squared plus nz squared. And now if we express this in terms of frequency, using the fact that f equals c over lambda, we see that f is equal to c over 2l multiplied by the square root of nx squared plus ny squared plus nz squared. We now want to use this expression to determine the density of states in our three-dimensional cube. We will follow the same logic as with the one-dimensional example that we considered earlier, in that we will try to count the number of states in a particular frequency range by considering axes along which we label the integer values of n. To simplify our calculation of density of states, we will consider a sphere with its centre located at the origin of the nx, ny, and nz axes. We will focus on just the positive values of x, y, and z, which represents 1/8 the volume of the whole sphere, and then use symmetry to complete the picture. Furthermore, we will consider a two-dimensional cross-section of the octant. Let's now look at this in a bit more detail. If we assume that our sphere has radius r, then we can determine the density of states by considering how many states lie between radius r and radius r plus dr, where dr is a small radius segment. We can express the radius of our sphere in terms of nx, ny, and nz using the following expression. We can then neatly combine this with the expression that we derived earlier for the frequency, and we see that the radius can be written in terms of the frequency as r equals 2lf over c. If we then differentiate this expression with respect to f, we find that dr by df equals 2l over c, and therefore dr equals 2l over c times df. So, what is nr-dr? Well, we see from our diagram that this will simply be equal to the volume of the small segment labelled dr, which for the whole sphere would be equal to the surface area of the sphere, 4 pi r squared, multiplied by the segment length dr. However, because we are only dealing with 1/8 the volume of the whole sphere, we need to multiply our expression by 1/8, and so we get nr-dr equals 1/8 times 4 pi r squared times dr, and this simplifies to pi r squared dr over 2. We can rewrite this expression in terms of the frequency rather than the radius by using the relationships that we previously derived. We find that nf-df equals pi over 2 times 2l over c all cubed f squared df, and this simplifies to nf-df equals 4 pi l cubed over c cubed f squared df. Again, we need to multiply this expression by 2 to account for the two possible polarization states of the electromagnetic radiation. And this now represents our final expression for the number of states that exist within a particular frequency range. Notice that the number scales with f squared, indicating that the number of states grows rapidly at high frequency or short wavelength. Now that we have an expression which allows us to count the number of allowed wave frequencies inside the cube, our next step is to calculate the average energy of each of these waves, and to this we now turn. In order to calculate the energy of each wave, Rayleigh and Jeans relied on a well-established result from the classical theory of thermodynamics, called the equipartition theorem. According to this theorem, if you have a gas at thermal equilibrium, comprising billions and billions of small particles in random motion, then the available thermal energy within the system will be, on average, equally distributed between the particles within the gas. Consider, for example, a box containing a monatomic gas, that is, each molecule consists of a single atom. In classical physics, you could think of each atom as a tiny sphere moving randomly within the box, colliding with other atoms in the walls of the box. In this case, the kinetic energy of each atom can be split into three modes, corresponding to movement in the x, y, and z directions. Given the incredibly large number of atoms within a gas, on average, the x, y, and z values for kinetic energy are the same. In other words, if you were to add x joules of energy to the box, then x over 3 joules will appear as increased kinetic energy in each of the three coordinate directions. For a system in thermal equilibrium, each mode or degree of freedom has an average energy equal to half kT, where k refers to Boltzmann's constant. You can think of Boltzmann's constant as representing the exchange rate between the currencies of energy and temperature. So, for example, a monatomic gas, which has 3 possible degrees of freedom corresponding to motion in each of the 3 coordinate directions, has an average energy of 3 times half kT, or 3 over 2 kT. To find the total energy of the gas, you would then simply need to multiply the average energy of each particle by the number of particles. This gives, in our example, the average energy times n. So, how does this apply to waves? Rayleigh and Jeans reasoned that the same statistical law should hold for the waves inside the cube. This is because the law of equipartition of energy was believed to apply to any classical system containing, in equilibrium, a large number of entities of the same kind. For the case at hand, these entities are stationary waves within the cube, each with 1 degree of freedom corresponding to their electric field amplitudes. Therefore, on average, their kinetic energies all have the same value, half kT. However, each sinusoidally oscillating standing wave has a total energy which is twice its average kinetic energy. In other words, the total energy is actually kT. This is a common property of physical systems which have a single degree of freedom that execute simple harmonic oscillations in time. It is worth pausing for a moment to consider where this result originates from. This will be particularly important later when we try to locate the cause of the ultraviolet catastrophe. The fact that the average energy is equal to kT has its origin in a more comprehensive result of classical statistical mechanics called the Boltzmann distribution. The Boltzmann distribution function provides complete information